Okay, so we're going to look at two sessions on oblique impact of smooth spheres. This is the first of those. The idea is you've got, we previously looked at objects, they collide with each other. Typically they've been single point particles. We haven't worried so much about the shape of the objects. And now we're going to generalize that slightly. So rather than thinking about two objects being particles when they hit and not thinking about their physicality, we're going to now extend that to considering smooth spheres. So it's still a big simplification. They're smooth, they're spherical, but it's a situation which is then a little bit more complex than a particle. Reason being, when two particles collide, you don't have to think about the angles at which they hit each other so much in terms of where contact is made. Where they make contact is going to dictate how they end up moving after collision. So now we're going to look at smooth spheres colliding, and that hence the title, Oblique Impact of Smooth Spheres. And then remember, oblique just means at an angle which is not head-on, not at 90 degrees. Okay, so to start off with, something to just think about. It's more of a geometry question, actually. You've got two spheres, seen here side on, so they just look like circles. They're resting on a horizontal surface, and they're touching. And the smaller sphere has a radius of 1, large sphere has a radius of 2. And then marked on the diagram, you've got the points A and B, which are the point of contact of each sphere with the surface, with the table or the horizontal surface. The question is, what is the distance from A to B? Give it a go. You can pause the video now. Okay, and in this case, I haven't noted down the answer, but let's quickly work it out. So what you should have done, most likely, is considered marking on the radius a few times, right? So that there is 1, and this here is 1 as well. And because of a fact that seems intuitive, which is that when these two radii, the number 1 radius and the 2 radius meet, they meet at right angles to the tangent of both of these spheres, and they kind of meet at a tangent line, right? There's kind of a tangent line going on here. And because radii are always perpendicular to the tangent line, that means we can actually just continue this line on perfectly straight like that. And that's length 2. And likewise, this purple line here is also length 2. And what we're interested in is this distance. But then that horizontal blue distance there is exactly the same as this horizontal blue distance here. And conveniently, this part here then in red is 1, which must mean if the whole thing is 2 vertically, this is also 1. And therefore we end up with a triangle that looks like this. If we color code it nicely, it's got hypotenuse 3, height of 1, and x, that's the thing we're interested in. So we just use Pythagoras, right? So then x is equal to 3 squared minus 1 squared is 8 square rooted. Which is equal to 2 root 2. Okay, and that's it. We got the answer. So just something to think about there. This idea that 2 root 2 is it's clearly less than 3, right? Because it's got about 1.41 times 2. It's about 2.8ish, less than 2.9. It's less than 3, which makes sense. So when two spheres are in perfect contact, just keep in mind that the distance that their centers are from each other will actually always be less than the sum of their radii. So 1 plus 2 gives me 3. That's the most it would ever be if they were in contact, and you were just measuring the distance between their centers. But if you're measuring it as a horizontal component, it's going to be less in this case. Cool. So we're going to just look at a few definitions now regarding this idea of spheres hitting each other and colliding. So we'll define a few terms and then we'll see how they're useful. So the two terms I kind of want to define are these, the line of centers and the common tangent. Whenever you've got two circles or two spheres on paper in contact, there will be a unique line of centers and there will be a unique common tangent, and they will be perpendicular to each other. To show you what I mean, let's just draw two arbitrary circles. Okay, I'm doing them at different sizes, although going forward they probably will model them as the same size. It won't actually matter, but the definitions work regardless of the size of the objects, if they're the same or not. So we might as well consider that when defining it. The line of centers is, simply put, the line, the infinite line that passes through the centers of the two spheres when they're in contact. Okay, so it's with respect to a specific configuration of these two spheres when they're in contact, right? The common tangent is then the, as we said, it's perpendicular, and it's the tangent to both spheres or circles passing through that contact point, right? Both lines will pass through the contact point. And it's quite convenient, they're always perpendicular by definition of the radius, or not by definition, but as a result of the radius of a circle always being tangent to the tangent at which the radius intersects the circle. And then we'll just label these, right? So this is, I'll just write for shorthand, LOC, line of centers, and CT, common tangent. That's not proper terminology, that's just my thing. You would want to write it out in full words in an actual exam. Line of centers, common tangent. And that's it. So any pair of spheres, well, let's do two that are the same size. Let's do them, say, like this. Again, we've got a center, that gives us the line of centers. That's our LOC. I've swapped purple and red this time. I shouldn't have done that, but never mind. And we've got the 90 degrees to that. Common tangent. Okay, so that's it. That's all that those two things mean. And then, yeah, one other thing I want to mention is when two objects hit each other, there's an impulse, effectively a change in momentum, which is what impulse is, and the objects will then move in some other direction. It's important to remember that the impulse always acts along the line of centers, which makes sense, right? That seems fairly intuitive. So I'm just going to draw that on each of these diagrams. You've got the impulse, capital I, and likewise an equal and opposite impulse here, because remember, momentum is conserved, so therefore change in momentum, which is impulse, must cancel out somewhere. So that's what it looks like on that diagram, and on this diagram we'll have an impulse here when they collide and an impulse here when they collide. Okay, so just keep that in mind. I haven't written any words on the screen to define these terms, but that's up to you to make in your notes. That should make sense. One of the lines goes through the centers. One of the lines is the tangent, the common tangent, passing through the point of contact. Okay. So now let's use those two bits of terminology to then break down how we're going to calculate the changes that occur when two spheres collide, right? So I'll draw two spheres, and to keep it simple, let's just make it so that the line of spheres is horizontal, or the line of centers, sorry. So that's our line of centers, and this is our common tangent. Okay, and again they're perpendicular, so that means we can use them effectively as axes by which we can split velocities into two different components, right? Just like with an analogy for this is when you have objects on a slope and we split it into the two components parallel to the slope and perpendicular to the slope. What we're going to use these two lines for is to split velocity into parallel to the line of centers and perpendicular to the line of centers, or parallel to the common tangent, which is the same thing, right? So we're basically going to consider this as one, direction there, line of centers parallel, and this direction, right, the common tangent parallel, and those are our two component axes, I suppose. Okay, and then what we're going to do with respect to each of these varies. So you'll initially probably be given the velocities of these spheres before they collide, and then you may know their velocities afterwards, or you have the reverse, but in some way or another you want to form equations which describe the relationship between the initial velocities and the final velocities, as we've always done, right? The u's and the v's, we relate them to each other. Now the general principle is what I'm going to write down now. Component of velocity, or velocities, because there'll be two of them, right, for each of one for each object. The components of velocities which are parallel to the common tangent, what happens to them? So this should hopefully make sense. It's much like when an object hits a wall. Remember we said only the component which is perpendicular to the wall is going to change, and we used to multiply by E when we had Newton's restitution. And the component of velocity vertical to the wall, we said it stays the same. So much like that, when the two objects hit each other, for both of them, the component of velocity which is parallel to the common tangent is going to stay the same. So we'll just write here does not change. Okay, so the velocity does not change in that specific direction, right? The component that's in this case vertical, but more specifically parallel to the common tangent. And then the other case we have is components of velocities which are then parallel to the line of centers. Now that's the more complicated one, and for that we can use our two favorites. Number one, use Newton's restitution, so that is E, and you'll use it just with the components which are in that specific direction, and likewise conservation of momentum. And as we've similarly done before, that will give you two equations, and usually in two unknowns, but then it depends on the type of question. Okay, but that's what you've got to play with. So what's parallel to this direction is easy, it doesn't change, and the components which are parallel to that direction of velocities, you need to use these two rules. Write them down, make an equation, and do the appropriate calculations. And that's it. That's the general principle, really, and that's going to underpin most of what we then do. So I'm going to run through two examples, and then you'll get a chance to do some questions. So let's look at the first of these. In doing this example, you'll also see how I suggest we create the diagram of what's going on. So we have a smooth sphere A, mass 2 kgs, and it's moving with a speed of 6, and it collides obliquely at an angle with another smooth sphere of mass 4 kgs. And just before impact, B is stationary Okay, and velocity A of A makes an angle of 60 degrees with the lines of centers of the two spheres. E is a quarter. Find the magnitude and direction of A and B, of the velocities of A and B after impact. Okay, so notice it said A makes an angle of 60 degrees with the line of centers. So effectively, they're not giving you the diagram, and you can draw it however you like. If you rotated the picture, it wouldn't affect what happens. So when it says the directions, we're going to have to talk about that in terms of it being respect to the lines of centers. So when we draw it, let's just pick the line of centers. The lines of centers. It shouldn't say lines of centers. It's a line of centers. We'll pick the line of centers to be horizontal. Makes it easier, right? So let's just draw the two spheres. And notice it doesn't mention anything about the size, but that doesn't matter because the result will be the same, right? It tells us the mass, but not the size. So just draw them as the same size. It doesn't actually affect the points of contact in this case, because we're always going to talk about this line of centers. Okay, yeah, that's my best attempt there. So then we've got the line of centers like this, and then let's mark on the other information. So B is not moving. This one's B, this one's A. B was not moving, but A was moving at a speed of 6 at an angle of 60 degrees. So what I suggest you do is draw in the velocity like this, and we mark that as 60 degrees there. Okay, and that is then 6 there, and we can also add its 2 kgs here and 4 kgs here. Okay, and that's all the information except for we also know E equals 1/4. Okay, and this whole thing we've drawn, this is our initial, right? This is before the collision. In terms of final, we're basically just going to draw the same picture, but the information will be slightly different, right? Specifically, the velocities will have changed. So when we look at collisions, we're always treating the initial and final as two instantaneous moments, which basically happen instantaneously, one after the other. The weights are obviously the same, sorry, the masses, which I suppose is equivalent to say they're the same. E is still a quarter, A and B are still the same object, but what's changed is the velocities, right? And the angles and their magnitudes. However, we shouldn't put on redundant information. Think about what's happening with this object B. When A hits it, which way do you think B is going to go? Think about it intuitively first. Is B going to go off at an angle? Is it going to just go off to the right? Is it going to angle down, angle up? So have a think what you think intuitively. And then after we thought about it intuitively, let's think about it mathematically according to the rules I set out before. It's going at 0 velocity, right? This object B. So in other words, it's going 0 parallel to the line of centers, and it's also going 0 parallel to the common tangent, which I haven't drawn on yet. So one of those directions doesn't change, and that's the one that's the component parallel to the line of tangents, the common tangent, right? So along the common tangent direction, its velocity does not change. So it was 0 before and it's 0 after. Therefore, object B is just going to move to the right along the line of centers, because as I said, the line of tangent direction doesn't change, it's still 0. So what that means is over here we can actually say for sure the velocity is just this direction, and we can just give it like a single unknown quantity. We don't have to worry about making it a vector. We can just say it goes straight to the right, and we can give it a label. I'm going to call it W, because I'm going to say V for object A. So then object A, we know one of the components, right? If we work out how to split this up, so hypotenuse 6, angle 60, so vertically we're going to have 6 sine 60, so that's 6 root 2 over 2, 3 root 2, and horizontally we're going to have 6 cos 60. 6 times a half will be 3. One of those doesn't change, and it's the one that's parallel to the green common tangent, so it's still going to be going at 3 root 2. So on the diagram, I'm actually just going to split into two components. I'm going to have 3 root 2 here, and now the only unknown is what is the horizontal or parallel to the line of centres component for A. So that we don't know. Let's just assume a positive direction to the right and give it an unknown quantity V, which could be positive or negative, right? So that's it. Now we've got two unknowns, V and W. And now with those, we can apply those two tools we had before, right? It's along the line of centres. We use conservation of momentum, and we use Newton's restitution rule. So let's do that. If we do Newton's law of restitution, that's E is equal to, and I'm going to treat V and W as being scalars that are either positive or negative, right? I don't know which way they're going, so they're kind of like one-dimensional velocities. I'm therefore then going to take right minus left, which is W minus V, and divide that by the left minus the right that it had initially. Now the initial left, which is A, was 3, and the initial right was 0, so it's just divided by 3, isn't it? So we get this. So 3 equals 4W minus 4V. Okay, and then conservation of momentum, that's going to tell us, well, the initial momentum, and remember we're only looking at the horizontal now, parallel to the line of centres, is 3 times 2, and that's it, it's 6. So let's put that here as a conservation of momentum. So 6 is equal to, and then what do we end up with? We'll end up with 2 times V plus 4 times W. Okay. So then a little bit of manipulation here. Add them together, and we get minus 6V equals minus 3, therefore V equals a half. So V is a half, and then let's just think about this line here. V is a half, so that's 2. Add that to the left, we get 5. 5 equals 4W. W equals 4/5. Oh, 5 quarters, sorry. 5 over 4. Okay, and that's it. So we can rub out here, that V and the W. That one's 5 over 4. And that one here is 1/2. And that's close enough to having the answer, really, isn't it? So B, magnitude is 5 quarters. Direction is along the line of centres, would be the only way we could put it, right? We can't say it's moving right because we assumed the line of centres was horizontal. It may not be. So we have to refer to the original reference points. So B is a speed of 5 quarters along the line of centres, and A is going to have a magnitude of this square rooted, which if we work that out, was that 3 root 2 or 3 root 3? Oh yeah, that should be root 3, shouldn't it? Because it's root 3 over 2 for the trig function, sorry. So that should be a 3. Okay. So then that squared plus squared, square rooted, should be root 109 over 4. in that case. So that's the magnitude, and then the angle, you just have to use a bit of arctan. So we've got effectively this. Say we're interested in this angle. This one's 3√3, this one's a half, therefore theta is equal to arctan of 3√3 divided by a half, or 6√3, which gives us 84.5 apparently. Okay, and that's it. And then you'd also have to say 84.5 degrees to the line of centers, right? So that you re-establish the reference point. Cool. Okay, so that's it for that example. Let's look at one more. Okay, so in this one they've kind of given us the diagram. We've got a small smooth sphere A, that's this one, mass 1 kg, collides with a small smooth sphere B of mass 2 kilograms. Just before the impact, A is moving with a speed of 4 meters per second in direction of 45 degrees to the line of centers. B is moving speed 360 degrees to the line of centers. Coefficient of restitution between the spheres is 3/4. So the only thing not on the diagram is that E is equal to 3/4. And we also might as well just draw in the tangent line. They don't seem to be quite touching actually, but assume they are in that diagram. Okay, what is the kinetic energy lost in the impact? Now, funnily enough, in the textbook, what they do is they work out the final velocities, the complete final velocities in taking into account the direction, and find the difference between that final kinetic energy and, you know, half mv squared, where they take 4 and 3. However, you could do that, but you could also just consider that if it's a difference, right, just a change in kinetic energy, then let's exclude the part of the velocity that doesn't change. So in this case, the components of the velocity which are, in this case, vertical along the common tangent, they're not going to change. So their kinetic energy associated with them isn't going to change. So we can just think about the horizontal case, right? The parallel to the line of centers case. So let's do that. Let's split up the components and just focus on that part. So in the first case, it's 45 degrees, so cos and sine of that angle are 1/√2, or 2√2 if you don't rationalize, times 4 gives us 8√2 here. Sorry, no, 2√2. Okay, yeah, 2√2. And then for the other one, we've got cos 60, so √3/2. Sorry, half times 3/2. Okay. So our initial kinetic energy, and let's just note it here, is going to be a half of m, which is in this case for the first one, a is 1, so that's a half 2√2 squared plus half of 2, that's 1, times 3/2 squared, which gives us 8 times a half, 4 plus 9/4, so 25/4. Okay, so that's our initial kinetic energy in the horizontal direction, right? Let's just make that clear, horizontally only. So there's actually more energy in the system, but that's what's going on horizontally. So now let's find what the final velocities will be in each case. So if I picture it as the after situation, or as the final, I'm just going to, again, treat them as like one-dimensional vectors. I'm not going to actually think about which direction they're going in. I don't know what that is, but I'll just declare that this one is V, this one is W. treat them as one-dimensional vectors. They could be positive or negative depending on the direction, but I'm taking right as positive. And then let's form equations with that. So first of these is going to be the E. I'm going to say 3/4 equals, so right minus left is W minus V divided by left minus right. But then we have to be a bit careful here because I said I'm treating these as like one-dimensional vectors. So we have to do the same here. That left one is going right. I took right as positive. So that's 2√2. And then this one here is going left, right? This 3/2 is actually a leftwards 3/2, so that's minus. So then left minus right is actually 2√2 minus 3/2. So I get plus 3/2 here. Okay. Remember, if you took V and W as just being scalars and you declare they're definitely moving to the right, then you might reinterpret this slightly differently. I don't like to think about which direction things are going in if I don't know for sure. So treat them as almost one-dimensional vectors, and I did the same then with these numbers here. So 3/2 is actually a minus 3/2. Okay, so cross multiply, and we're going to get 6√2 plus 9/2 equals 4W minus 4V. Then let's do conservation of momentum. So this was E. Let's do conservation of momentum. We have 2√2 times 1. And this is all, remember, momentum just in the horizontal direction. And we've also got 2 times 3/2, which is 3. Except not 3, because momentum, remember, we're taking everything as vectors, the direction matters. So that 3/2 again is really a minus 3/2. Probably better to have just written it in. So it's actually 2 times minus 3/2, and I get minus 3. Okay, so that's the total momentum initially, which will be the same as the final, which in this case will be V times 1 plus W times 2. Okay, and then from there we just need to do a bit of simultaneous equations. I'm going to be a little bit lazy and save us all some time, because we should know how to do simultaneous equations. V and W, let's just write down what they end up being. In this case, we solve simultaneously. You should get minus √2/3 minus 7/4. I believe textbook has that as positive, but that's only because I declared V as going in no particular direction, but right as positive. So now we know actually the left ball ends up going left, which makes sense. And then W, we end up getting 7/6 minus 5/8. And that is a positive number, isn't it? So that stays going to the right. Okay, and then kinetic energy lost. What we're going to have to do is probably want to store on your calculator. Let's just call that, I'm going to call that capital A, capital B, and our final answer is going to be 25/4, which is the initial kinetic energy, minus the final kinetic energy, which is 1/2 times 1 times A squared plus 1/2 times 2, which is 1 times B squared. So here I'm just lazily writing out what we would finally put into the calculator, where A is that number V and B is that number W. You put that in the calculator, you work it all out, and we should get about 2.73-ish. Okay, and that's the kinetic energy lost. The kinetic energy, as we said, going vertically hasn't changed. So the kinetically loss overall is still 2.73. And that's our answer for A. And then part B is quite fast actually. What's the magnitude of the impulse exerted by A on B? So remember, impulse goes along the line of centres. By A on B, so we're looking at that direction. It's this one here. So what is this I? In other words, what's the change of momentum of B? And the change of momentum of B, well, this is actually easy because we've just stuck with horizontal, haven't we? So we've got that W there, which is the final velocity of B. And we're just going to take that away. From that, we're going to take away the initial. So we've got a half m, which is 1, times b minus, and what was its initial for b was 3. Sorry, hang on. This is, let's correct this slightly. By quite a bit actually. It's b, which is the, what was that, the w going to the right, but we had 3 over 2, not 3, I wrote 3 there, and also it's in the opposite direction, so it's minus 3 over 2, remember, so that's b plus 3 over 2. So that's the change in velocity. It was going minus 3 over 2 and then b the other way. The change in velocity is b plus 3 over 2 times its mass, which is 2, which we didn't need to halve. So 2 times this b value plus 3 over 2. And that gives us, if we work it out on the calculator, 5.049. And that is the impulse exerted by A and B. So we've got the final answer for part B. And that was ours for part A. Okay, so that's it really. We're just going to be using the same tools we have before, but just to a different sort of problem. It does mean you've just got a different diagram to add to your sort of toolkit. This concept of the two spheres with the liner centres and the common tangent. Draw them the same size. You won't ever have, as far as I know, you wouldn't really have a problem where they're different sizes, because even if they were, it doesn't affect the mathematics of the problem at all. Circles are circles. They always hit each other at the same place, which is along their line of centres and at their common tangent. They don't have any other choice because of their circular nature. Okay, so let's look at some questions for you to try, see if you can give them a go. So I've got 2 questions for you to look at. First one is probably easier than the second. The first one is mainly to just try a question similar to one of the examples we just went through, and make sure you can calculate it, get the right answer. The second one is a bit more tricky, and I think will be a nice test of you having understood the concept and also testing your confidence on being able to follow through on the calculations. Because in question 4 there, you're not actually given many values, you're just given various unknown quantities. So it's down to you to make sure you've really understood the relationships between all those and that you can apply the formulas. And you can't rely on simplifying it to a number at any stage because you haven't been given really any numbers. Definitely want a nice diagram for 4. Also, perhaps just a small hint for 4, don't forget that you've got a few basic identities such as sine of 90 minus theta equals cos of theta, and likewise cos of 90 minus theta equals sine of theta. Things we should know, but that we might sometimes forget. I think you may need to make use of that in 4. Okay, so it's just these 2 questions. Hopefully I've left you with enough time, otherwise borrow a little bit from the second half. So I'll let you give those a go. You can pause the video now.